This is part 6 in a series of videos about stardust. In this episode, we're going to learn about how stars actually lose mass to the surrounding space. So, how do stars lose mass? Well, let's first think about what a star is. It's a big ball of gas, and it is densest in the innermost region. And as you move out from the core towards the surface, it gets lower density. And then at the surface, it doesn't just stop, it has an atmosphere. And so the gas just gets lower and lower density. A star has an atmosphere. Now, can it hold on to the atmosphere, or is it just going to drift off because it's too tenuous? Well, let's investigate that idea. How do we determine whether an atmosphere will be lost or retained? That is, whether it's a star or a planet or a moon, it's going to follow the same rules. Now, we discussed this in another video, but let's just review it here. Here I have a Maxwellian distribution. This is the equation for the Maxwellian distribution. This is speed on the x-axis and the number of particles at that speed on the y-axis. And what you can see here is the thermal velocity is the peak of this distribution. So there are more particles moving at this speed than any other speed. But there are also particles moving more slowly and particles moving faster. And those particles are moving faster. It is an asymmetric curve. And so what you have is it goes off to infinity. So the actual average speed is going to be somewhere over here. What really matters is, do the atoms or molecules have enough energy or speed to escape? And then what matters is the escape velocity. And so what I've got here is, this is at a speed of 0.5 kilometers per second. And so if my escape velocity was 0.5 kilometers per second, then most of the atoms would have sufficient energy to escape, and so they would. What you can see here is, if the escape velocity is all the way down here, and this is nearly 5 times more than that thermal velocity, then there's only a small number of atoms that have the energy to escape. Some of them will escape, most of them will be held onto. So this is the idea that we can work out what atoms or molecules should be held onto by a planet or a moon or a star. Now, in order to get there, we need to understand what the average kinetic energy is. So remember, kinetic energy is just half mv squared. And for a gas, the average kinetic energy of a particle is 3/2 kT, where K is Boltzmann's constant and T is the temperature. We can then take this and work out what is that speed that things are moving at. So the average speed for our particles is this VRMS, the root mean square. The average speed is given by this equation here. So it's the square root of 3 kT upon m, where m is the mass of the atoms or molecules that are moving. Okay, so how does something hold on to an atmosphere? Well, we need to consider the escape velocity. So here I've got the equation for escape velocity. That is the square root of 2 gm upon r, where m is the mass of the star, planet, moon, whatever is holding the atmosphere, and r is its radius. As we mentioned in the previous slide, if the average speed of the atoms is close to the escape velocity, then the gas can escape very easily. But we also know that for moons like Titan and Triton, they hold on to some molecules that give us a framework for what is the criteria for holding on to atoms. So Titan, for instance, has formaldehyde in its atmosphere. Triton has methane in its atmosphere. So based on the temperatures and masses and radii of those two moons, we know that basically molecules are going to be retained if the escape velocity is more than about 5 times the root mean square, or average velocity of the gas particles. So we can make that our criterion. We need to have the escape velocity greater than 5 times the average speed. But remember, the average speed is given by the square root of 3 kT upon m. So I can plug that in, and I just squared both sides so that I get rid of the square root. And so I've got 2 gm upon r must be bigger than 75 kT upon m. And I can rearrange that. And this now gives me the temperature. And it says, for a planet or star or moon of mass m and radius r, for it to hold on to atoms or molecules of mass little m, it has to have a temperature below this number. Now, one other way of thinking about this is, at a given temperature, what is the size of the atoms it can hold on to? So I've just rearranged this equation. So now we have it so that for a star of mass m, radius r, and temperature T, this equation tells us what the size of the atoms are that it can hold on to. Now, remember that when we're talking about stars that lose mass, we're talking about things that are after the main sequence. So the sun is not losing that much mass right now. But when it becomes an asymptotic giant branch star, it's going to have a radius about 500 times what it is now. And so that's going to affect the gravitational pull. And so here we've got that equation again for this is the mass that can be held onto. And we've got the radius and the temperature. But now if we're looking at the sun and it getting bigger, the radius has just got a lot bigger. And so we should be able to escape more material. So I've got a temperature of 3000 Kelvin. That's the typical temperature for an AGB star. The mass is going to start out as about 1 to 8 solar masses. And the luminosity is about 10 to the 4 solar luminosities. So from this, we can work out what the radius of the star actually is. We can do this by taking the Stefan-Boltzmann law. Basically, the luminosity is 4 pi r squared sigma t to the 4. And I'm just dividing out by the sun, so it'll be in solar units. My 4 pi's are going to cancel. There were sigmas that canceled. We end up with an equation that looks like this, and I'm going to rearrange it to give me the radius. So here I've got the radius in terms of solar radii, and I can calculate it from the stellar luminosity and the stellar temperature. So what's the radius of the star? I can plug in my 10 to the 4 solar luminosities. I can plug in my temperature at 3000 Kelvin, and this is the temperature of the sun. And what I get is that the star is going to be about 370 solar radii. When we increase that radius to such a high number, we're going to end up being able to lose more material. So let's just plug in some numbers here. We've got star, 3000 Kelvin, 1 to 8 solar masses, 10 to the 4 solar luminosities. The radius is 370 solar radii. I put in the mass of the sun and the radius of the sun in metric units. If we plug it all in, what we find is that for a 1 solar mass star, it will hold on to stuff that is more than 1.8 mu in mass. So that means everything that's not hydrogen. If it is more massive, so at the high mass end, you'll actually end up with something that is able to hold on to everything. So not even hydrogen is going to escape. So even though this star is much, much bigger than it was without having more mass, it is not able to just let the material drift away. It will still hold on to it by gravity. So what gives? Well, there's pulsation. So what we have is that stars in the AGB phase, their brightness changes over time. And what's happening is they're pulsating, they're moving in and out. And we're going to go into this in a little bit of detail. What's happening is their brightness changes over time. Here we've got the light curve for Omicron Ceti. Omicron Ceti is Mira. We've talked about Mira already. Mira is the archetypical AGB star. On the x-axis, we have dates. So this is the 1st of January 2011. This is the 1st of January 2012. So each of these is 6 months. And here you've got the brightness in magnitudes. Above about 6, it's visible. So you can see that Mira is visible for part of the year and then disappears and then comes back again. You can see that the time from one peak brightness to the next is about a year. So you can see that every year it gets brighter and dimmer and brighter again. And this is down to the star literally getting bigger and smaller, getting fainter and brighter, getting hotter and cooler. What's going on in pulsation? Well, we talked about this in a previous video, so I just thought I'd show this view graph again. But basically what's happening is you have an area where it is opaque, and so it's absorbing the radiation. And as it absorbs that radiation, it gets hotter and it will expand. As it expands, it's going to cool and change its opacity, and it's also going to be lower density, and light can get out. Because the light can get out, it's no longer as opaque. It's going to cool again. Gravity is going to win over pressure, and so it's going to shrink back down again. So we start the cycle over again. Now, normally you would expect that a star would be able to find an equilibrium between pressure and gravity, but for stars in a certain area of the Hertzsprung-Russell diagram, they cannot achieve hydrostatic equilibrium. And this is called the instability strip. And we also have these long period variables here. In this region, the problem is that you're having a phase change, that the pulsation happens because of helium that is ionized going to doubly ionized helium. Normally in stars below about the A class, so cooler than about 10,000 Kelvin, the helium is going to be neutral at the star's surface. But as you drop down into the star, you'll find a region where there is a Hg+, that is, it's hot enough to ionize helium. And below that, you'll have a region that is He2+. If the star contracts, the density and temperature at the helium plus layer increases. But as it increases, there's now enough energy to knock another electron off. And so the helium plus goes to helium 2 plus. But when it goes to helium 2 plus, the opacity increases. And that means that it can absorb more light that's hitting it. And so it will expand. And as it expands, it will cool down. As it cools down, the temperature is decreasing, the energy is decreasing, the electrons will start to recombine, and your He2 pluses will go back to He plus. But now you're back to He plus, and you go back to the beginning. And so it's because as it shrinks, it becomes He2 plus, and as it grows, it becomes He plus again. It's never able to find an equilibrium. And so this is why these stars pulsate. So why is pulsation important? Well, as it pulsates, you have the surface of the star moving in and out. So you're adding to the thermal velocity of the atoms with the motion of the surface of the star. Now, when we talk about pulsation, we can measure this in various ways. So here I've got, this is actually for a variable star that's not an AGB star, but the same ideas apply. This is a much shorter time scale, so it's on the time scale of days. For our AGB stars, it's months to years. But here we can see this is apparent magnitude. So this is basically brightness. And we've got a star that's going up in brightness and then down again and then up again. And we can monitor the star and see how its brightness changes. We can also monitor the star's temperature by looking at the spectrum. Remember, we work out a star's temperature by looking at the spectrum of the surface of the star. Now here you can see that the temperature is going up. It's actually hottest when it's brightest and coolest when it's faintest. This makes sense because remember, we've got the Stefan-Boltzmann law. And so the flux goes as T to the 4. So as you increase the temperature, you increase the flux of energy a lot. Now that same spectrum that allows us to get the temperature, it has all the absorption lines from the atoms in the atmosphere. And what we can get from that is the Doppler effect and see the radial velocities. And so here you can see something moving towards us pretty fast. So it's outward from the star, but then it's slowing down and it stops. And this is where it's stopping, expanding outwards. And now it's moving back in, it's moving away from us, it's moving fastest down here. And now it's going to go back to moving slower and slower outwards until it stops again. And now it's moving back towards us again. And so this is also something we can monitor. And then if we have interferometry, we may be able to measure the diameter directly, but we can certainly get the diameter out from the temperature and the luminosity. Remember, luminosity equals 4 pi r squared sigma T to the 4. So if we have the temperature and the brightness, we can figure out what the changes in radius are. So we have this thing that's moving in and out. And the important thing is that it's got a range of speeds where it's adding to that thermal velocity of the atoms. What is the magnitude of this pulsation? Well, it's changing a lot throughout this course of the AGB, and it's not entirely clear what happens with this pulsation. We have two different types of AGB stars. We have Miras, named for Mira, which is the archetypal one, and we have semi-regular variables. So here, this is actually the light curve for Mira that we already saw. And typically, Miras will have a large amplitude pulsation. That is, the change in brightness is more than about 2.5 magnitudes. It will also have a longer duration. This one's about a year, but anything from about 2 months up to about 3 years is possible. Whereas for the semi-regular variables, they will tend to have a smaller change in brightness, and it will be less regular and often shorter in period. But it's hard to give it a proper period because it's not a nice regular curve. Okay, so what effect does this pulsation have? Well, we've got the escape velocity, and we've also got now this push. So we can work out the escape velocity. This is for Mira. Mira is 1.2 solar masses. It has a range of radii from 332 to 402 solar radii. And so we can work out, just plugging into here with the two different radii from minimum size to maximum size, what the escape velocity is. The escape velocity ranges from 33 kilometers per second at minimum, which is when it's largest, and to 37 kilometers per second at maximum when it's smallest. But now let's consider these pulsations. When it is largest, it is moving outwards. The material is moving outwards the fastest. And when it is smallest, it is moving inward the fastest. And so what we have is something that is adding to or subtracting from the thermal velocity. And so we need to recalculate. It's not just that we have an escape velocity of about 35 kilometers per second. At maximum light and minimum light, it's going to be affected by this pulsation. So here's my escape velocity again, and here's the average velocity. Remember, this is the 3kT over m. But now we're going to add in the velocity of the surface of the star. The surface of the star is moving outwards towards minimum light and inwards towards maximum light. And so what we get is now an effective speed where we can add together the RMS speed and the radial speed of the surface. So we can actually make that into a new equation. So instead of saying that we need our escape velocity to be less than 5 times the RMS speed, and I've rearranged this. Remember, before we were talking about retention, now we're talking about atmosphere escape. So if my average speed is 5 times the escape velocity, that should help to make it escape. But now I'm saying, actually, I want to add in this surface speed effect. So all I'm doing here is adding in, here's the escape velocity, here's the VRMS. At minimum light, we're going to have VS is positive. At maximum light, it's negative. Remember, we already worked these out for Myra. And so if we add in, and I've just added 10 kilometers per second in each direction, what we get is that the thermal velocity now to escape, to get away from the star, is only 23 kilometers per second at minimum light and 27 kilometers per second at maximum light. So this is basically that same equation that we just had. And now I've rearranged it so that we can get out what is the mass of the things that can escape. I've got my temperatures. Remember, at minimum light, it's cooler than at maximum light. So that cramps it a little bit because the atoms will be moving a little slower. And it helps a little bit, but we still are only getting 3 AMU of mass able to escape. That anything more massive than that is going to be held on to. So hydrogen can escape, but helium can't at maximum light. At minimum light, helium might just escape if it's this lower mass isotope. So it is easier to escape at minimum light, but that's not telling the whole story. So we need something else. What is that something else? That something else is dust formation. So here I've got my AGB star. The star is pulsing. It's pulsing at the surface. That pulsation is pushing material up. So I want you to consider, if I want something to escape from, say, the surface of the Earth, and I've got a ball and I'm going to throw it up in the air. If I don't throw it very hard, it's not moving very fast, it's going to not get very high. The harder I throw it, the faster I throw it, the higher up it's going to get, until eventually I give it enough speed to escape. But as it gets higher and higher, it's also going to get colder and colder as it goes up in the atmosphere. This is true for the star's atmosphere too. So my particles, although the pulsation isn't enough for them to achieve escape velocity, it is enough for them to get much higher away from the surface of the star where it is cooler. And that means that there are temperatures where dust can actually form. What you get is at some distance above the star, dust will start to form. Well, now you've got things that are really massive and you'd think that they would be pulled down, but they're not. Dust is much more effective at being pushed by radiation than gas atoms are. And so that is what comes into play next. We've formed some dust and radiation pressure is going to act on them. So remember, in a previous video, we talked about radiation pressure. Basically, I've got here, this is the flux of light from the star, this is the cross-sectional area, and this is the speed of light. And so I've got a force of radiation on my dust grains. And the thing is, the dust grains can absorb all the light that hits them. They may not, it depends on their albedo, but atoms are not very good at absorbing all the wavelengths of light. So they don't absorb all the photons, because they can only absorb the photons that allow electrons to jump from one level to another or change their vibrational rotational state in a quantized way, whereas a solid can absorb every single type of photon. And so that's why it can be pushed more effectively. Okay, so I've got this radiation pressure, and I can compare this to gravity, because now I've got to worry about gravity's trying to pull my dust grain down, radiation is trying to push it out, and they're acting in opposite directions. And so I can work on the ratio of the force of radiation to the force of gravity, and I end up with an equation like this. One of the things that I then want to do for stars is to convert this into a luminosity. So remember that luminosity is 4 pi r squared sigma t to the 4. So I can get rid of my sigma r squared t to the 4 and put in an L and throw in a 4 pi. And so here I've got something in terms of the brightness of the star and the mass of the star, the density of the dust grain, and its size. For an AGB star, we have a luminosity of 10 to the 4 solar luminosities. And so we can plug that in and plug in all the numbers. This is converted so that the mass would be in solar masses. And this is the size of the dust grain and density of the dust grain. And so now we can use this to work out what should be going on with our dust around our AGB star. So here's that equation again. Now in this case, I'm actually going to use the radius and the mass and the temperature. So I've got the temperature of Mira at minimum light. I've got the radius of Mira at minimum light, and I've got its mass. And so I can plug all of that in, and what I get is an equation like this. Now, if we assume that our dust grains are about 2 kilograms per meter cubed, we can talk about where that number comes from in the future. If that's a reasonable number. Then what we get is we can put that in and we can work out, okay, what is the size at which radiation pressure starts to lose? And it turns out that grains up to 2.5 millimeters across, that is actually 5 millimeters across, a radius of 2.5 millimeters, will be able to be pushed out. That is where the balance of the force is going to be with radiation and not with gravity. And so that means that as soon as you start to make dust grains, they are going to be pushed out really fast. As they are pushed out, they will drag the gas along with them. They are stealing momentum from stars' light. The stars' photons have momentum, they're absorbed by the dust grains, and that's what pushes them out. But then they collide with gas atoms and transfer some of that momentum to the gas atoms. And so we get material flowing away. As soon as dust forms, you're going to get that pushed out. And then you're going to get another wave of pushed out. Now, it may be a continuous process, but it is going to be affected by the pulsation of the star, because that affects how high you can levitate the atoms and molecules in order to make the solids that the dust is comprised of, that is then pushed on by radiation pressure. So to pull this all together, here I've got the asymptotic giant branch. At the beginning of the asymptotic giant branch, the star is cooling down toward 3000 Kelvin, and it continues to cool all the way through this phase. At the same time, it is getting brighter. That means it's getting bigger and bigger. So I have something that's getting bigger and cooler, and it's also losing mass. A star that starts at 1 solar mass is going to lose about 40% of its mass. A star that starts at about 8 solar masses is going to lose more than 80% of its mass. And so that is going to affect the escape velocity. The escape velocity is going to go down because your mass is decreasing and your radius is increasing. This means that more mass can be lost over time. And it also means that dust formation can happen closer to the surface because it's getting cooler. And so what you're going to get is material that's receiving more light because the star is getting brighter. It's getting more material pushed out, and so the mass loss rate is going to increase. And so we start with something that it doesn't make much dust, and the dust is being pushed out, but it's not forming super close in, and it's not that thick yet. And over time, it's going to get more and more dense closer in. So it's going to form closer, and you're going to make more of it. And so the dust close into the star is going to be really, really dense as you get towards the end of the AGB. And that's where we're going to leave this topic.